All right, so what we have is this white powdered solid, and it looks very homogeneous. So can you say it's pure,
No.
this unknown, because it looks homogeneous? No, actually it could be a mixture, a mixture of two different white powdered similar looking substances. So to try to determine is this pure or impure, we actually don't have to do that. What we could do is we can analyze this, and if it's a pure substance, and pure substances are going to have a fixed percentage of sulfate in there. So for example, sodium sulfate is going to have a different percentage of sulfate than lithium sulfate. And so we could do that, but that's assuming if it's pure. If this were a mixture, then it can have any amount of sulfate in there. It's not going to be fixed. But we don't know if it's pure or mixture. So can you tell me a way that we might be able to determine if this is pure or mixture? What are some of the ways you might try to figure out if this were pure or mixture?
Dissolve it and try and precipitate the sulfate.
We could dissolve it and try to precipitate out the sulfate, but it could be a mixture, and that would work as well. Or it could be pure, and that would work as well. It could be a mixture of two different soluble sulfates, like for example, sodium sulfate and potassium sulfate. Both are soluble. Both would dissolve, and it would free up the sulfate, and then you can precipitate out the sulfate, but it can't tell you. You could tell by maybe the percentage. What we could do is we could try to figure out what is the percentage sulfate here, and then look at the database of every sulfate compound in existence, and then compare. Does it match with any of those? If it doesn't match with any of those, then likely it's a mixture. Or maybe it's a new compound. We don't necessarily know, but are there other ways to determine? Well, one way is dissolving. Sometimes you have a mixture and one of the compounds is soluble, the other's not. Or you could have more than two components. You could have multi-component mixtures. And so we could try dissolving it and see. That might give us clues. Are there any other things we could do?
Molarity? Try to find molarity?
Well, molarity is just, again, molarity in itself would be a mixture. It's a mixture of some compound in water and how many moles of that substance you put in water. And so that's not going to be unique in the sense that you can make a 1 molar solution of many different things. And so, let me tell you a common way that's done, and it depends on how easy it is to melt the stuff. A common way is you put this under a little microscope, and the microscope's attached to a little heater, and then you heat it up, and you see, if it's pure, what tends to happen is it just has a very sharp, what we call a sharp melting point. That is, you hit the melting point like ice. When you hit, let's say it's colder than 0 degrees C, you warm it up to 0 degrees C, and then it melts, and it stays at 0 degrees C. And we get a sharp melting point because ice melts at 0. It doesn't start melting does it start melting at 0 and finish melting at 5 degrees C? No, it just stays at. Okay, with a mixture, what tends to happen depends on the components in the mixture. And so it depends on how many impurities. When you get impurities in ice, what happens is that tends to break up the hydrogen bonding interactions that hold the ice together, let's say. So this is dirty ice. What tends to happen there is it starts melting before 0 and doesn't finish melting until a higher temperature. So you get a melting point range. Usually the melting point range, the wider the melting point range is, the less pure it is. And so this is a very common analysis. They use it in organic chemistry. So we have melting point apparatus next door over here to determine the purity of your crystals, and also to help identify what those crystals are. Sometimes you have different components. Let's say one thing melts at 200 and the other thing melts at 300. And so what happens at 200, all that stuff melts and there's still solid left in there, and you got to ramp up the temperature until the rest of it melts. And so melting point is one. Otherwise, it's kind of hard to determine, is this pure or mixture? And so the other means that we have for solids like this is they're usually crystalline. And so we have some technique called X-ray crystal diffraction or crystallography. And what you do is you shine X-rays at it. And the way the X-rays scatter gives a fingerprint of the substance. So for example, sodium sulfate would have a different fingerprint, X-ray fingerprint, it's called X-ray diffraction fingerprint, than potassium sulfate. So you'd see the fingerprint for sodium sulfate in there, and you'd see the fingerprint for potassium sulfate. And then what we can do is it's quantitative because the way light interacts with matter is quantitative. We'll talk about that more later. And you can determine what the percentages are easily, depending on how intense the fingerprints are. So that's another method. And then there are other methods as well, using light's interaction with matter. And the light's interaction with matter is spectroscopy. So we could shine not just X-rays, we could shine visible light. And so if we dissolve this, we can analyze, not for sulfate, but we can analyze for certain metal cations like potassium ions and sodium ions, that kind of stuff. All right, so what we want to do is we want to figure out how much sulfate is in here. Now, are all sulfates soluble? Not all sulfates are soluble. And so one of the problems we run into is if it doesn't all dissolve. The first step in our analysis is we got to get this unknown solid to dissolve. And so if it doesn't dissolve, what can you try to force it to dissolve? Are there certain ways you think you can get something that really is hesitant, really? What things could you try to get it to dissolve?
Could we heat it up?
You could heat it up. That's
To
probably the
help
most common thing.
Break the bonds.
Right, it just helps. Things tend to be more soluble in hot water than in cold water. And so this is the first thing. If it doesn't dissolve in room temperature water, we try heating it up. What if that doesn't work?
What if we try adding another compound?
Yeah, we could try adding another compound like what?
Soluble salt.
Well, we could try, because sulfate, what's one of the properties of sulfate?
The smell.
Like chemical properties.
Oh.
We know like metathesis, sulfate, you can't really, it's odorless, so you can't really
Is
smell
it?
it. So, but there are certain compounds that do have an odor, like sulfuric acid. Sulfate itself, like if you had sodium sulfate or potassium sulfate, you wouldn't smell it. At least I can't.
It reacts with acids stronger than bisulfate.
Yeah, this is going to react with all acids stronger than bisulfate. So one of the next steps is if it doesn't dissolve in room temperature water, it doesn't dissolve in hot water, we try adding acid. We try to dissolve it in acid. And hopefully that attacks the sulfate in the lattice and breaks it apart. The sulfate's a base. Bisulfate's not a great base, but sulfate's a good base. Not strong, but there are other things that that people potentially try to dissolve things, and it depends on how much you want to preserve what's there. So people, if let's say it doesn't dissolve in acid, sometimes you try base. Sometimes base will dissolve it. If this is an unknown, you don't know what's inside it. So we try water, hot water, acid, base. And then we go, if it's still not dissolving, then we go a little bit more extreme. So we try like a hot oxidizing acid. What would be an example of a hot, well, we could try mineral acid first. Mineral acid, give me an example of a mineral acid you could try first. Hydrochloric, that's the most common. People try that, hydrochloric. First you try dilute, you don't want to go. Then you might try more concentrated. If that still doesn't work, then you want to attack it not with a mineral acid, you probably want to attack it with a oxidizing acid. But you got to be careful with the oxidizing acid, it could just decompose everything, react with it, oxidize it. You aren't going to be able to oxidize sulfate though. But we try oxidizing acids, we try hot oxidizing acids, like hot concentrated nitric acid, see if it dissolves there. Or on the other tack, maybe it's not an ionic compound. You know, maybe it's a molecular compound. If it's a molecular compound, then what we try is we try water, alcohol, and some non-polar organic hydrocarbon. Do you know any non-polar organic hydrocarbons? Non-polar organic hydrocarbons would be like methane, but methane's a gas. That's not going to work so well. Ethane's a gas. Propane's a gas, liquid at elevated pressure. Butane, you know, is gas liquid. Pentane's a liquid. So we could try pentane, but the most common one's hexane. And so we try hexane, 6 carbon, and see if it dissolves in there. So we go polar, water, semipolar, alcohol, nonpolar, hexane.
Oh.
Hexane. Another solvent that's commonly used is benzene, but benzene was banned for maybe a decade. It's a potential carcinogen, and so people weren't using that. And benzene was one that was commonly tried. But you know, you guys are lucky because it's going to dissolve. It's going to dissolve easily. But that's not to say in the future you won't have this headache of trying to get your sample to dissolve. That happens. And so what we can do now is we can look. There's some things that we can observe here. We observe the color. What is the color? Well, it's white. And the form. What is the form? Yeah, you know, usually we just call it powder, white powder. You know, or it could be like a paste, you know, or it could be big crystals, little crystals, etc. So in this case, it's a white powder. We wouldn't just say white, you know, because white could be different things. It could be a white liquid, although there aren't that many, etc. We have to give it a form. Solid powder. Well, powder implies it's a solid. So we don't have to say solid necessarily. But that's it. All right, next, what else can we determine? Well, we can determine the mass of this. Just weigh it. When we weigh it, which balance should we use? Should we use the centigram balance? This is called the centigram because this is the 1/10 of a gram, that's the 100th of a gram. 100th of a gram is a centigram. So should we use the centigram balance?
No.
Or should we use the more expensive 1/10 of a milligram balance?
1/10 of a milligram.
Yeah, we're going to weigh it to the nearest 1/10 of a milligram.
Accuracy is key.
Yeah, accuracy and precision. We want to get the highest accuracy and precision. Although this is the highest precision, do we know it's accurate?
No.
We don't know it's accurate until we do what? We need to do what step to make sure it's reading accurately?
You gotta tear it. You gotta zero it out.
Well, even if we tear it, it still might not be reading accurately.
We gotta calibrate it.
We got to calibrate it, right? And we calibrate it with what are called standard masses. And we buy these standard masses. They aren't, you know, you could buy very expensive standard masses. We have the moderately expensive standard masses. I think it was like $200 for the set. And so we just can go over there and just make sure it's reading properly. So when we zero it, we put the standard mass on there, 10 gram, 100 gram, whatever, and see if it's reading. If it's not reading correctly, then we'll adjust the calibration on it to make sure it's reading correctly. You don't have to calibrate the balances. The balances have already been calibrated for you. The other thing that could cause it from not reading correctly is if the balance is not level. The balance has a little plunger that goes in and it records the mass here. If it's tilted a little bit, then the force is not going straight on the, I think it's some kind of spring or some pressure sensitive sensor there. Part of the mass, if it's tilted like this, part of the mass is resting on the sleeve. And so you're going to get an inaccurate mass. And so the other thing we look for is to make sure the balance is level so that all the mass goes on the detector. Otherwise, you could be getting an inaccurate mass as well. The accuracy is very, very important. So these are the things we can get. So we know how many grams this sample is. We just got to figure out how many grams of sulfate is in there. Now, the thing is, this is a solid, so the sulfate is locked in some lattice, and this could be a mixture or it could be pure. We don't know if it's a mixture or pure. We aren't going to answer that question. We're just going to determine what the percentage of sulfate is in here. All right, so the first thing is we want to free up the sulfate and then isolate it. And so fortunately these are water soluble. But before we do that, we have to weigh these. And weighing is not as easy because some of these solids are hygroscopic to some degree. Some of them are not, some don't pick up water, but we don't know. We don't know what's in here, so we got to treat it as if it could pick up water and form a hydrate. And so what we're going to do here is you're going to get a sample. This is called a weighing bottle here. And the weighing bottle is, if you leave this open to the air, then all this humidity here is going to saturate the crystals here. Even though they don't look wet, they could pick up water molecules, can get stuck in what are called void spaces in the crystal lattice. There's little gaps in there. And so I don't know, if this is a hydrate or not. And so what we're going to do is we're going to treat it as if it is a hydrate. And so what that means is this. We're going to dry these first. Well, fortunately you don't have to dry them because they've been drying in the oven probably since last week. And so these have been heated. Now to dry these, we just heat it up above like 100 degrees C. That should be enough to drive off any waters that are stuck either on the surface of the crystals or in the void spaces of the crystals. But the thing is, if you take this out of the oven and it starts to cool down, what's going to happen?
It's going to condense.
It's going to reabsorb the water. We don't want it to reabsorb the water. And so when you remove this from the oven, we need to cool it down in a humidity-free environment, and that's this. This is called a desiccator here, and in the desiccator we have desiccant. And this desiccant that we're using here is dryerite. Dryerite is a hygroscopic solid. It loves water as well. And so this is, I think, calcium sulfate. It's calcium sulfate, and then they put a dye on there. So if you see blue, that means it's dry. If the blue turns to pink, can you see some of these are already pink? That means that's saturated with water, and it's not going to work anymore. So once this turns all pink, we throw this in the oven and get it all blue again. This is the desiccant. So what we're going to do is we're going to allow it to cool in the desiccator. Now the desiccator has what's called a ground glass joint. The ground glass joint is just a very smooth glass surface here. And it provides an airtight seal, but there's grease here, and so like for example, if I do this, take a look at that. You see, it's because the grease holds it there. So when you remove the lid, you can't pull it off straight. You just slide it off, and then it comes right off. And so what we need to do is we need to cool our samples in the desiccator. To do this, our samples are going to be hot. Okay, make sure there's no rust on your clamps here. And what we're going to do is we're going to take off the sample. We're going to put the lid in here first, and then put our sample in there. You can fit about 4 samples in here, so we don't have enough desiccators for everybody. And then seal it up. And we'll just let it cool inside the desiccator. Here. All right, once this is cooled, then we're going to remove our sample. There's dry air in here, and so when we take this off, I'm going to remove the sample bottle here. I'm going to put this on. Now, I can handle these with my fingers here. If I'm weighing this is called a weighing bottle. If I'm weighing this, I don't want to handle it with my fingers because each time I touch it, I'm leaving residue on there. And with a 1/10 of a milligram balance, you can actually weigh the residue that you leave on there. But we aren't going to be weighing it with a weighing bottle. That is just too much work. And so it asks you to weigh the weighing bottle, right? Don't bother weighing the weighing bottle. It asks you not to touch the weighing bottle with your fingers. You could touch the weighing bottle with our fingers because we don't care what the weighing bottle weighs. So if you look at page 1-9, it says mass of bottle and sample, mass of bottle minus sample. Do you see that? Yeah. Ignore those first two. We're just going to weigh out the samples. Okay. So weighing out the samples, you know why they have weighing bottles? They have weighing bottles because it depends on the balance you have. Some balances cannot tear a beaker, it's too heavy. Our balances can tear a beaker, it's no problem. And so people used to have to use weighing bottles because the most of the balance could tear were a few grams. And that wasn't enough. And so what we do is we'll just tear or zero the beaker and then tap in the sample that we need. So what you do is you don't want to leave the cap off for extended periods of time, otherwise it's going to reabsorb the water. So when you're ready to weigh, you'll remove the cap and then tap in some sample in here. You don't have to get it exact. About how much do you need?
0.3 to 0.4 grams.
Okay, 0.3 to 0.4 grams, but weigh it to the nearest 1/10 of a milligram here. And so anything around there. Hopefully you don't overshoot too much. How many samples do we need? 3 samples, okay. I think we have to work with partner with this lab. Is that correct? Yeah, I don't think we have enough equipment. So we'll be working with a partner. All right, again, we can handle the weighing bottle. We're not going to weigh the weighing bottle and the sample or any of that. We're just going to weigh our sample directly in a tared beaker. We don't need to know how much this bottle weighs. Okay, once we have our sample in the beaker, then what do?
We dissolve it.
Yeah, we dissolve it. And are we just going to dissolve it in just water, or are we going to add acid, or what are we going to do?
We're going to test it. Add acid.
Are we going to add acid to this?
No, we're going to add water.
We're just going to add water?
We should start with water, yes.
All right.
Water and then acid.
Okay, how much HCl are we adding?
2 milliliters of 6 milliliters.
Okay, the acid is not to help dissolve it. These samples dissolve fine in water. The acid is serving a different purpose. Do you know what the purpose of the acid is? The purpose of the acid is for the next step, which isn't the dissolution step. And so once we dissolve it, what we're going to have is we're going to have a aqueous solution that contains sulfate ions plus other stuff. We don't know what the other stuff is. Now what we want to do is we want to isolate the sulfate from all the other stuff. How can we separate the sulfate from everything else?
By adding,
Yeah.
by precipitating it out.
Yeah, we're going to precipitate it out. And so what's the precipitating agent that we're going to use?
Barium chloride.
Yeah, so we're going to use barium chloride for this. BaCl2. Chlorides are all soluble, except for silver, lead, mercury, so this will be soluble. This is going to be an aqueous solution. And so the barium and the sulfate, you know, the metathesis reaction, barium ions like sulfate. And we're going to precipitate out barium sulfate. And so we can separate out the sulfate from everything else. But does barium like any other ions? What other ions does barium like? Tell me all the ions that barium will precipitate with. If it's only sulfate, then we have nothing to worry about. Yeah. Barium likes carbonate.
Phosphate. S2OH. Carbonate and phosphate.
Yeah. Carbonate, phosphate, and what was the other one? Is there another one? Chromate? Yeah, barium likes chromate. But carbonate and phosphate are colorless. Chromate, do you know what color chromate is?
Is it a white powder?
No.
Green.
Chromate's going to be yellow. Well, it could be, it depends on what else is in there. It could change the color. So we could get some clues. In the aqueous solution and in the solid, does it have any color? If it has color, then likely colored ions like chromate probably aren't or may not be present. But if there was chromate present, yeah. Chromate would precipitate. What else does barium like? Sulfide? Sulfides are all insoluble except for group 1, ammonium, and group 2. Barium is a group 2, and so sulfide's not going to happen here. Most of the time it does happen. Sulfides are very insoluble, and sulfides tend to precipitate, but just with the group 2 it doesn't. In group 1 it doesn't. Everything else it does. What else? How about hydroxide? Hydroxides are all insoluble except for group 1, ammonium, and calcium, strontium, and barium. So barium hydroxide won't precipitate. What else? Well, think about the insolubles. The hydroxides, sulfides, and carbonates, phosphates, and chromates. I think that's it, right? That should be it, yeah. Now, there's some other chemical properties of this. What we're going to do is we're going to add excess acid to this. Let's add some. In the next step here, we're going. Actually, in this step, this is the reason why we're adding HCl. And so in step 1, we're doing the precipitation. In step 2, we're adding the HCl. So now we're going to do this plus the HCl stuff. And so I'm going to write it over here. These are our precipitates here. So if I take barium sulfate plus HCl, what will I form? Now this is going to be double replacement, so we're going to go all the way. And so in this case, we're going to form what? Yeah, barium chloride and H2SO4. We'll need 2 HCl's for this. Now, barium chloride, is that a precipitate? Or is that soluble? It's soluble, so that's aqueous. And then sulfuric acid is an acid, and so we're looking for driving force. Are we going to have a driving force? Yeah, maybe we have a driving force. Are we going from a stronger acid HCl to weaker acid H2SO4? No, we're not, because of the leveling effect. The leveling effect is going to tell us that these are going to be equivalent. And then what we say is we're just going to say there's going to be no reaction, NR. There's no driving force. There's no gas formation. There's no precipitate. There's no stronger to weaker acid. And so if we put in HCl in here, we're not going to get any reaction. Does that make sense?
Yes.
It's a little bit tricky, but because we're going all the way to sulfuric, not bisulfate. If we're going to bisulfate, then yeah. Seems like it, but this is the way we're going to analyze it. My metabolism. How about barium carbonate plus HCl? What will form here? Well, we're going to get barium chloride again, plus carbon dioxide and water. Yeah. Or carbonic acid. And so we'll need 2 HCl's for this. Is there driving force here?
Yes.
Yeah. Stronger to weaker acid plus gas formation. So this will effervesce. So if we did generate any barium carbonate precipitate, that barium carbonate precipitate will be dissolved, and in the process we're going to form CO2 gas. How about with barium phosphate? Okay, so what will we form if we add HCl to barium phosphate precipitate?
Sodium chloride.
Barium chloride again, and hydrogen phosphate is also known as phosphoric acid. Is there driving force here?
No.
Yes, there is driving force because we're going from a stronger acid to a weaker acid. And so we have driving force. So let's try to balance this. So I have 2 phosphates, so I'll need 2 phosphoric acids. And 3 bariums, so I'll need 3 barium chlorides. And that's going to give me 6 HCl's here. And so if barium carbonate, barium phosphate form, both of those will dissolve in acid. We just got to make sure we have enough acid to completely dissolve those, whereas the barium sulfate remains. Now, how about barium chromate? Again, we're going to form BaCl2, but in this case we're going to form H chromic acid, H2CrO4. Chromic acid. Is chromic acid one of the 7 common strong acids? No. So again, we have driving force here. We're going from stronger acid to weaker acid. And to balance this, we'll need 2 HCl. That should do it. All right, in gravimetric analysis, this is called analytical chemistry. In analytical chemistry, these ions here are called interfering ions, or interferences. And we have these interfering precipitates. These are going to interfere with our analysis. And so what we're doing is we're removing interfering ions from our analysis by adding HCl. And so this is the purpose of the HCl, is to remove these interfering species. This is not as dark. It's not to help dissolve it, it's to get rid of the interfering species.
So should we not add the HCl before the barium?
It doesn't matter. It says to add it before, right?
Yeah.
It's adding it before to remove these preemptively. And so it's taking a proactive rather than a reactive approach. But it doesn't really matter. If you take the proactive approach, then by adding the HCl, if there's any carbonate in there, just attack the carbonate directly rather than the precipitate. So it's probably better to add it before rather than after, but the purpose is to tie it up. So we're going to tie this up as CO2 and water, and this is going to be converted to phosphoric, and this is going to be converted to chromic acid, I think, or the precipitate. But in reality, it doesn't matter if you add it before or after. These are very reactive with acid, so I usually add it after. Try to maximize the precipitate. All right, and so what you're going to notice here is when we do the precipitation, this is going to get so cloudy. The crystals are tiny. The crystals of barium sulfate are tiny. And these tiny crystals are easily suspended by water. You know, big crystals fall down to the bottom of the beaker. You know, big crystals are always nice. As big crystals form, they fall. But when these tiny crystals form, they form what's called a colloidal suspension. It's like and so we end up with a suspension. What it looks like is it looks like milk. You can wait, you know, a day, a few days, a week. You know, if we left this white suspension in our drawer and came back next week, most likely those crystals will all have settled. But we don't want to wait. We want to speed it up. And so what we need to do is we need to get those tiny particles to coagulate. We call it coagulation. We need them to coagulate into bigger particles, and those bigger particles can fall down to the bottom of the test tube due to gravity. So how can you get these tiny particles to coagulate? That is, to kind of clump together. We're going to heat it up. Not cool it down, but heat it up. Heat it up to get those tiny particles to collide with each other so that they can coagulate. That's called digestion. And so in order to get rid of this white suspension here, we're going to digest the samples. This is a common trick done. So we heat it, and so we'll get the hot plates going, and then you can kind of get it to a soft, gentle boil, and then give it a little bit of time, and then what we'll have is we'll have the precipitate collect down here at the bottom. And so hopefully we're going to leave, what are we going to leave? We're going to leave chloride ions. We know chloride ions are in here because we added barium chloride and HCl and other stuff. And hopefully at the bottom of this we're going to have our barium sulfate solid precipitate. All right, the next step here is we're going to separate the barium sulfate from all this other stuff via filtration. We have different levels of filtration. We have qualitative versus quantitative. Do you know the difference? What's qualitative versus quantitative?
Quantitative is measured.
Yeah, quantitative is measured, exact. Qualitative is just approximate. So it depends on the filter paper. Some filter paper, is qualitative. That is, the pores on the filter are kind of big, and some of the tiny crystals make it through. I mean, we're going to have some tiny crystals. Some of the tiny crystals make it through. What we need to do is something more quantitative. We're going to use filters that have very small pores so that we capture even the tiniest of crystals. But the problem is it goes so slow. And so this is why most of the time we use qualitative, because it's just so much faster. We can do gravitational filtration. But we aren't even going to use paper. We're going to use these. These have a little what we call fritted disc on the bottom of this. This is a glass disc which is porous. If I pour water in here, and watch the bottom of this. It's not even wet yet. You know, if you were to just sit here and wait for this water to filter through this, you'd have to wait maybe 2 weeks or a week or something. It's too slow. So what we're going to do is we're going to suck the water through the disc here. So right now you can't even see a drip rate. Nothing's dripping out of this. And it's filled with water. And so we're going to do this. We're going to do what's called a vacuum filtration. And this looks like an Erlenmeyer with a little sidearm here. This is called a filter flask. And the filter flask is so you can connect the vacuum hose to this. Then we have this. This is a crucible adapter. So we're going to put this into our filter flask like this. And make sure the seal is very tight here so that there are no vacuum leaks. And then we're going to put our crucible, filter cellulose crucible on top of this. And again, make sure there's no leaks. So this is our setup here. And then we're going to attach this to the vacuum. We're not going to attach it directly to the vacuum because if water gets sucked into our vacuum system, it's going to hit the pump. When it hits the vacuum pump, if there's water there, it'll destroy our vacuum pump. And to prevent that from happening, we're going to set up a trap. And this trap is if water gets sucked into the vacuum system, it'll get sucked into the trap here, down through here, and collect at the bottom. And then the vacuum comes out through this hose here, through the sidearm. So let me just attach this to the vacuum. Let's see. It's pretty weak vacuum, but it's better than nothing. So we'll just go with that. All right, so the vacuum's pulling through this sidearm here. Do you know what this thing is on the top?
No.
This thing is a vacuum release. It's just a little screw clamp. And so if I unscrew this, you hear that? It's a vacuum release. This is just to break the vacuum. Because once we set this up, let's see, you might want to clamp that so it doesn't tip over. That's a pretty decent vacuum, right? You want the better the vacuum, the faster this is going to go. So we just make sure everything is nicely sealed. This has got to be upright, otherwise water could get sucked into the trap. Okay, now I'm going to put my cellulose crucible on there. And now it's pulling through there. So let's see what kind of drip rate we have now with this. Get some water here. I might have to clamp that or put that in a big beaker. Let's see. I don't have any big beakers. All right, so this is under vacuum here. And so I'm going to pour some water in here and let's see the drip rate now. Okay, so that's drip, drip. Oh, now it's going faster. Do you see that drip, 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 drip? Do you know how many drops are in a milliliter, roughly?
I think there's like 10.
Close. Not 10. 20 drops in a milliliter. So it depends on your drip rate. If your drip rate is going drip, 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 that's too slow. It's going to take you forever to filter it. And so normally what we do is we do a quick check to see our drip rate. But you don't want to do the check for the drip rate because when we capture our precipitate in these, it's very difficult to remove the precipitate out of this without leaving some behind. And so this is it. I want to I want to see how much barium sulfate I form. If I know how much barium sulfate I formed, then all the sulfate and barium sulfate came from our original unknown. And so I can use some stoichiometry to calculate that. But I need to weigh that. And so this is what we're going to do. These are weighable. And so what we're going to do is we're going to dry these. We're going to dry them because these ceramics like to pick up water on the outside, and this is glass. Glass loves water too. And so it'll pick up moisture. So we're going to dry these, and we don't weigh hot objects. We weigh room temperature objects, otherwise we set up convection currents and it makes it very hard to weigh. And so the same thing's going to happen with these that happened with the unknown sample. You're going to collect these out of the oven, and then you're going to dry these inside the oven and then cool them inside the desiccator. Okay, once we cool these down, then we can weigh them. And so we'll take these out of the desiccator. These ones you don't want to handle with your fingers. The weighing bottle you can handle with your fingers. These ones we need to handle with tongs or paper towel or something that we don't leave fingerprint residue on there. And then we'll throw these into the beaker and then weigh them individually. These should be marked. Do you see there's a little marking on the bottom there, written in pencil? This is Celis crucible number 1. They forgot to mark this one. It's okay. Okay, now I'm going to remove this one, but in order to remove this, this is under vacuum, you know, and so like I could pull this here, but it's not going to come off easily. Well, in case it does, I'll catch it. And so what we do is we turn off the vacuum, and then I'll use this relief valve here to break the vacuum. Okay, and then I can remove it easily. But again, do I want to handle this with my fingers? I could, as long as I wipe my fingerprints off before weighing it. And so that's normally what I do. I'll just handle it with my fingers and then get a Chem wipe it off, and then put it on the balance. Or you don't handle them at all with your fingers. That's to, let's do this. So anyway, you're going to get these hot out of the oven. You're going to cool them in the desiccator, and you're going to weigh them. Okay, once they're weighed, then do you really care if you handle them with your fingers? No, because we'll clean them off later, next time we weigh it again. And so once you weigh this and you know the dry mass and it's clean, then we're good. And you got to make sure you can keep track of these because each of these weighs a different amount. And so I have 2 1s and a blank. So I got to probably mark it with a pencil or something. Okay, now for vacuum filtration, let's see. What you want to do is you don't want to mix it up. What you want to do is you want to filter as much of the clear liquid as possible. Otherwise, if you mix this up and get a suspension and then start filtering, you're going to clog it even faster. And so we try to pass as much of the clear. You know what we call this clear liquid here? It's actually, it might have a color. If there's chromate in there, it could be a clear yellow solution, or it could be a clear colorless solution. Do you know what we call this? We call this the precipitate. What do we call this solution? It has a name. Actually, it has a couple of names. Oh, the solute? No, not the solute, but it starts with an S. Supernatant. Yeah, kind of a weird name, but this is supernatant. That's the liquid part of this. We try to pass as much of the supernatant through crucible as possible. Let's show this short video, 2-minute video on vacuum filtration technique. Their setup is a little bit different than ours. This is now, gloves are normally worn now in school labs. In fact, at UCLA, it's required. You have to wear gloves. Everybody has to wear gloves. Here, it's optional still.
Using rubber hosing, we need to collect the correct type of funnel. In this case, because we're collecting a large amount of solid, we're going to use a bucket funnel. Ensure that the rubber bung on the bucket funnel fits snugly in the conical flask. Then make sure you've got the correctly sized filter paper for the funnel.
This is qualitative here. They're just using some qualitative filter paper.
This should fit over the holes inside the funnel. You can now pour in your mixture of liquid and insoluble solid. The beaker containing the mixture can be rinsed once again. The collected solid can then be rinsed further with distilled water. Once your product is dry, you can turn the vacuum pump off. Then remove the rubber hose to release the vacuum, and the funnel can be removed from the conical flask. Finally, the filter paper and solid can be placed on a watch glass. The solid can then be scraped from the filter paper.
Yeah, this is typical. They left some solid in there. They're probably going to scrape that over there as well. And so then you could either scrape this off and weigh it separately or do what else. But we're doing it a bit differently than this is the standard vacuum filtration technique here.
Vacuum filtration is a fast and effective way to filter many chemical mixtures. Some materials you will need for successful filtration include a beaker with a mixture, a stirring rod, rubber policeman, filter paper, and a wash bottle. Always make sure to check that the filter assembly is working correctly before use by turning up.
This is kind of interesting because their vacuum is made by a water aspirator. And so it just creates a vacuum when you flow water through a tube, and then you have a little side arm there. They're using a trap, and the previous one, which is that one was from the Royal Society, they didn't use a trap. And so you have to be very careful when you don't use a trap that you don't destroy the vacuum pump. They had a little vacuum pump on the side there.
On the water.
Okay, this funnel here is a Buchner funnel or Buchner funnel. And this is for large quantities of precipitate, and you just need a qualitative. We're using the Celis crucible for the quantitative. They're also using rubber policemen. We have rubber policemen here, so you might be wondering what you do with rubber
To
policemen.
position the filter paper correctly, place the filter paper in the beaker funnel and vacuum paper. Use the same solvent that is in the mixture being filtered.
Now this is a technique they missed in the last video. Usually what we do is we wet the filter paper so it sticks to the bottom. If you just dump in your supernatant and precipitate, there's a chance that the filter paper can lift up and then your precipitate can go underneath the filter paper. So this is important.
For a high school lab, this is usually water. Start adding the mixture right away before the filter paper dries. Decant about half of the liquid first by pouring it down the stirring rod onto the center of the filter paper.
Okay, do you see, now she's trying to get all the supernatant or through the filter paper before.
Stir the mixture and then pour the remaining into the funnel.
I wouldn't do that. They're creating a suspension there, and that's going to slow down filtration. I would have decanted as much of the supernatant as possible
And then-
before doing this.
Yeah. That's what it tells you in the lab.
Oh, does it? Okay, that's good.
Then use a rubber policeman to transfer the rest of the solid into the Buchner funnel.
That's fine. That's the job of the rubber
Transfer any
policeman.
remaining solid by rinsing all materials with the solvent, which in this case was water.
Are we rinsing with water?
Only the eye one.
No, we
But then
prepare a
it's
wash solution.
What's inside the wash solution?
It's 200 milliliters of hot distilled water to which 10 drops of 6 moles of hydrochloric acid.
Yeah. The wash solution is, normally it's DI water, but in this lab it's going to be a little bit different. We're going to use, hot, so we need to prepare our wash solution. Our wash solution is going to be just slightly acidified water. It's going to be a slightly acidified rinse. And that's to prevent interfering species from interfering, potentially interfering species from interfering. And so let's take a proactive approach to get rid of those interfering species. What you can do is you can put it into a rinse bottle, or you can just use a beaker and then wash it. It's important to wash because our precipitate is going to be contaminated with our supernatant solution. Our supernatant solution contains all these other species. We got to make sure we get rid of all those. We don't care about contaminating our precipitate with HCl because HCl is easy to get rid of. How do we get rid of HCl? Just heat it up. If you heat it up, HCl is normally gas. It will come off. That's how we get rid of the HCl. But if we had, let's say, sodium chloride, then you can't just heat it up and vaporize the sodium chloride. It's not going to come off, or whatever else is in there. And so HCl is the contaminant that we can live with because we're going to just bake it off anyway. In this case, it's very important that we don't leave any precipitate behind. We want to get as much of the precipitate as possible. This is a quantitative analysis lab, so we've really got to try to get 100% yield if possible. So we're going to use our rinse solution to wash any remaining precipitate in there and to wash off the crystals. And then we should use some additional rinse to rinse off the crystals
precipitate
further. So I would have given another rinse or two to make sure that there's no residual supernatant contaminants left. Because once we dry these, all those will come out of solution and give us an error.
As desired. Then release the vacuum and turn off the water flow. It is important to equalize the reduced pressure of the filtrate
They're using a pinch clamp, which is a lot easier than our screw clamp.
assembly before turning off the water flow to the aspirator.
That's a waste of water, so we don't do that anymore. We just
When
use
correctly
mechanical
using lab
clamp.
filtration, it can save quite a bit of time, both in the filtering and in the sample dry time.
All right. So what we're going to do after this step is we're going to vacuum filter and collect our barium sulfate here. But we want pure barium sulfate in here. So we're going to make sure we rinse this thoroughly. So once we have that, then our barium sulfate is going to be wet with what? It's going to be wet with our wash solution. If it's wet with our wash solution, that's fine. Like I said, we're going to bake off that wash solution. How we're going to bake off that wash solution is we're going to put all these into our beaker. The beaker is going to have a number on here. This is beaker number 10. Then we're going to get a ribbed watch glass like this, put this over this, and then put these into the drying oven next door, right here. And then come back. When we come back next week, then we're going to weigh these. So we'll know the mass before and the mass after, and then we can figure out how many grams of barium sulfate we collected. Okay, any questions? No? All right. All right, so you're going to work with a partner, and then you're going to go collect your unknown sample and whatever else you need. I think. But the unknown samples are going to be hot, and so you'll have to get a desiccator. Probably get a desiccator. And I think you'll need. Do you have a ceramic plate?
No. Oh yeah.
Okay, bring a ceramic plate and a pair of tongs. And you're going to get your unknown sample in a beaker.
I actually had a question for that.
Yes.
How do I clean the rust off of my tongs? These are like covered in so much
Yeah,
rust that it's almost brown.
yeah. Try to scrape it off as best, or just here, exchange them. You can exchange them with these.
Oh, I can get yours. Let's go.
You can leave me your rusted ones.
Let's say I can probably exchange it with the office.
Or there's a box of tongs over there, I think. All right, when you go get your unknown, the unknown number's written on the beaker here, and they're going to be hot. So bring a ceramic plate, put it on the ceramic plate, and then hold the top down with either paper towel or tongs. Like this, so it doesn't fall off. There might be beaker tongs back there. Beaker tongs are even better because beaker tongs you can just grip it like this. These are crucible tongs. Crucible tongs aren't made for holding beakers. Oh, those are beaker tongs right there. So, you could use those. I'll explain.